In 1958, a man named Charles Keeling began recording CO2 concentrations at an observatory in Hawaii. The Keeling curve, as it is called, shows that CO2 concentrations have been steadily increasing since that time, from 316 parts per million in the late 1950s to over 400 parts per million today. A concern associated with the increase in CO2 concentrations and related temperature increase is what will happen to the Antarctic ice sheets. We can get an idea of what's going to happen from modern observational data from satellites and weathering stations. But these records are rather limited in their time span. We need a timescale of thousands to millions of years in order to estimate how the ice sheets responded to past warming climates. To do so, we use paleoclimatology, the study of Earth's past climates. Changes which occurred in the past are recorded in natural archives, such as ice cores, tree rings, corals, and sediment layers, and we can use those records as an analogy to future climate changes. For my research, I'm focusing on the Antarctic ice sheets. At its thickest point, the Antarctic ice sheet is 4,800 meters thick. This is more than 1,000 meters taller than Mount Fuji, and is taller than the Rocky Mountains in Colorado. If the entire ice sheet were to melt, global sea level would rise 60 meters. So if even a small portion of the ice sheet were to melt, there could be global repercussions. In order to see how the ice sheet responded to past warming climates, I am analyzing samples from a marine sediment core for beryllium-10, an isotope produced in the atmosphere and deposited with precipitation. Beryllium-10 collects on the ice sheets, and it eventually is stored within the ice. So when temperatures increase, the ice melts and the beryllium-10 is released and settles onto the sediment. We can then back calculate how much meltwater was needed to release that amount of beryllium-10. Now, analyzing the samples is actually quite difficult since the concentration of beryllium-10 is to the order of parts per trillion. For an idea of how small that is, that's about 30 seconds out of 1 million years. So to extract this incredibly minuscule amount of beryllium-10 from the sediment, I am using a new method and cutting-edge equipment with chemical reagents here at Auri. The sample is then analyzed using an accelerator mass spectrometer, also at the University of Tokyo. The equipment and utilities here at Auri are applicable for a wide range of experiments and analyses, and we are using these to increase our understanding of the Earth's past climate through the study of paleoclimatology.